Okay, so let's do the second part of chapter 1 right now, which is the codes. I said we would learn two different codes. You'll learn ASCII code and BCD code. So binary coded decimal is reminiscent of when we did hex conversions, but mostly you're going to take your 4 binary bits and you're going to convert it into its decimal value. And that's particularly useful for things like clocks. So I have a clock time right here, 10:37:49, and I'm kind of showing it graphically in binary. So a 4 is 100, a 9 is 1001. So we have ones right here, right? Ones and zeros. And that's a 9. The 7 is 111. 3 is 11. 0 is all zeros, and a 1 is all 1. So what you're really doing, for example, let's say the number 49. 49 in base 10 equals what in binary coded decimal. So it's binary coded, so it's been encoded into a binary number, but the coding is this in a decimal format. So it's really reminiscent of like if you were a kid and you did secret codes. But for example, a 4 is 0100, and a 9 is 1001. And so I just converted 49 in base 10 to a BCD number. And this will be particularly useful, as I said, for 7-segment displays. So notice there are 7. You need well, there's always, well, this one doesn't show 7. These all show 7. So a digital display, like I showed you earlier, like displaying some kind of a number. It all depends on which one of these segments you light up. For example, this is a number 7 right here, right? So BCD is used a lot to control these displays. So anyhow, moving on ahead. Let's do a few more examples. Write 496 in base 16 as a BCD number. Now, which would be the best way to do that? Well, there's not really a one-to-one mathematical conversion right here, but what we can do is convert the base 16 number to, well, we have to convert it to decimal no matter what, I think. And then from decimal, we can convert it to BCD, but we have to get it to decimal. I don't see another way around it. And again, there's more than one way you could do that. And I was thinking, just sitting here thinking, why did I do that problem? It's actually the problem in your textbook has 496 to the base 10 that you want to convert to BCD, which is a little nicer number. So let's actually do it that way. Now, no reason why I couldn't go base 16, but I'd have to convert it to base 10 before I can convert it to BCD. So a little bit annoying there, I guess, to have to do that. But let's do the base 10 to BCD. So a 6 is a 0110. That's a 6 because, right? This is 4, 1 4 and 1 2. That makes 6. And 9 is a 1001. That's 9. And 4 is 0100. So that's 496 in base 10, 496 converted to a BCD number. So now the other way around, here's our BCD number, and we want to convert it to a base 10 number. So this number right here is an 8. This is an 8. This is a 4. This is a 5. And this number here is a 7. So 758, base 10. Question for you. Can I convert this number? Is this a BCD number? By the way, I think this is a midterm question. Is this a BCD number? No. Why is it not a BCD number? It's invalid. I guess you could just say it's invalid. Invalid BCD. Because this number is 8 plus 4 plus 2, that's 12. This is equal to the number 14 in base 10, which is also number E in hexadecimal. And 14 isn't a decimal number. You can't, it's not valid. I can only represent the numbers 0 through 9 with BCD. So BCD actually uses up more bits than other encoding does. So you cannot represent, see, 1-4 has to be represented with 8 bits. 1-4 has to be 0, 0, 0, 1. So 14 in BCD is 0, 1, 0, 0. That equals 14 in decimal. This is not valid. It's not a valid BCD encoding. So, summary, here's all of the different both numbering systems, and BCD is not really a numbering system, it's really encoding that we have covered so far. And so I did point out that BCD uses up in general more bits than any of these other numbering systems do. But it has its advantage. We'll use it from time to time in this course. One more encoding is ASCII. So every time you type, which stands for American Standard Code for Information Exchange, every time you type something on a keyboard, a letter for example, a letter isn't stored in memory. It has to be stored in your computer somehow as a binary representation, a series of ons and offs in transistors inside your computer, inside the memory. So you have to encode the letter G, for example, into something binary. And we use 7 bits to encode every single character on your keyboard, including spaces and backspaces and returns. They all have an encoding. So, for example, if I want the letter capital G, and I want to see how it's encoded into your computer, it says my most significant bits are this, so it's 1, 0, 0, and my least significant bits over here are 0, 1, 1, 1. So this is the letter G, how the letter G is encoded in your computer. Notice it is 7 bits long, not 8, but usually you end up putting a leading 0 in front of it. So there's always a leading 0 in the most significant bit portion so that we have a byte of information. This is now a byte. So that's ASCII encoding. So one of your homework problems is that you have to either encode or decode something from binary to ASCII or vice versa. And basically you have to just look it up on the table. So an example your textbook has, we'll go over just to make sure it's understandable, how digital might be a useful way of measuring something in the physical world and then storing it in a computer. So I have four tanks, A, B, C, and D, and I guess they have, it says it has geothermal electricity generation facility, so maybe you have hot water in here. I don't know, maybe you have hot water. But in any case, you have to measure the pressure, you have to measure the temperature of each one of these tanks. And pressure and temperature are an analog signal. So what has to happen is, like pressure here, pressure from tank D goes to this point, and temperature from tank D goes here. And these things are all in parallel. And the computer is going to come through and get this pressure. What if this pressure said 87 units, whatever the units of pressure are, torr, that would be really low pressure. Let's say pascals. You probably use pascals. So maybe it's 87 pascals is the pressure of this tank. So that number 87 has to be converted into something binary. So we can convert it, that's in base 10. We can convert it to a hexadecimal number. We can convert it to a binary number. Keeping in mind hexadecimal is really converts to binary inside your computer, and that binary value from each one of these different ports is sampled one at a time and stored inside your computer. So basically the important thing is that your analog signal has to get digitized into digital for each one of these things, and then the word is multiplexed together by your sampling system. Okay, you have a problem like this in your homework. It is a good review problem, and so I'm going to refresh what Tuesday's lecture is by going over this problem, which is sort of all encompassing, and then you guys can go off to the lab and do your first lab. So the first row is done for you. Let's say it's samples from our system on the previous page, and it records a value of 59. So for example, maybe tank D, value A, sample A is pressure on tank D. So it has to be converted to decimal, and so there's a value. I mean, it is decimal, it's an analog value right now, but it has to be sampled and converted to binary. It could be converted to BCD if you were doing a display, and the binary value, of course, can be written more efficiently in hexadecimal. This reading a bunch of zeros and ones is prone to error in reading it, error in writing it down. But if I convert it to especially a hexadecimal number, it's more concise and less prone to be making errors. So first row is done for you. Basically, you have to fill out everything in the row. So here's problem A. I'm given the value in hexadecimal, and I have to fill in all of the other values. So let's do A first. So I have 44 in base 16. Well, I can pretty much immediately write that in binary. So 4 is a 0, 1, 0, 0, and another 4 is a 0, 1, 0, 0. So there it is in binary. 0, 1, 0, 0, 0, 1, 0, 0. I can write it actually very easy in octal as well. But let's convert now to 44 in base 16. Let's convert it to decimal. So a decimal number, this is, we need 2's as weighting factors. So that's 1, 2, there's a 4 there. There's not an 8, there's not a 16, there's not a 32. However, there is a 64. So 64 plus 4 is 68. So we know that this is 68 in decimal. Easy to convert to BCD from there. So BCD, a 6 is 4, 5, 6. And an 8 is, that's an 8. So there it is in BCD. 0, 1, 1, 0, 1, 0, 0, 0. Octal. So octal, yes, this is not a valid octal right now. So we'll convert next to, yeah, the only one I'm missing now is octal. So we'll convert next to octal. So that's taking the binary number and grouping it in groups of 3 instead. There's my pen. So I'm going to group this in groups of 3. So this is base 10. This is BCD. And group it in groups of 3 is 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, and 1, 0, and then a 0 in the front. So this is a 4, a 0, and a 1. So it's 1, 0, 4 in base 8. Okay. Well, I don't need to put the base 8 because it says octal on the header of the table. So that's basically how you are going to do. You have a similar problem. We can go through each one of them. I guess I'll do another one because it's a good review. BCD, this is a BCD number. 1001 1 1 2 3. So this is an 8, this is a 9, and this is an 8. So that's a 98 in decimal. So now I have to make, which one would be the easiest one to do next? Let's make 98 be in hexadecimal. So an 8 is oh, that's interesting. Cool. All right. Actually, maybe not. So 98, let's convert 98 decimal into binary next. I think that would be the easiest approach to do. So 98 into binary, you can do it by subtracting the weighting factors out of it. For example, I can see that 64 will come out of it. 128 won't, but 64 will come out of it. We can do it that way, or we can do it the divide by 2 way, and you know I'm fond of divide by 2. 98 divided by 2 is 49, remainder 0. 49 divided by 2 equals 24, remainder 1. 24 divided by 2 equals 12, remainder 0. 12 divided by 2 equals 6. Remainder 0. 6 divided by 2 equals 3. Remainder 0. 3 divided by 2 equals 1. Remainder 1. And then the last one down here, 1 divided by 2 equals 0. Remainder 1. So my answer is 1, 1 with, this is the MSB down below, most significant bit, 1, 1, 0, 0, 0, 1, 0. So now I have my binary number 1, 1, 0, 0, 0, 1, 0. If I want to convert this to octal, I divide it into groups of 3. So this is a 2, this is a 4, and this is a 1. 1, 4, 2 in octal. If I want to convert it to hex, I group it into 4s. 0, 1, 0, 0, 0, 1, 1, 0. So I group it into 4s. This is still a 2, but this one is a 4. This is a 6. So 6, 2 in hexadecimal. So the process continues. Now, I'm going to show you a cool tool that you can check yourself. You can check your answers. However, when you take your midterm test, you have to be able to do all of this by hand. Your midterm test will be in class and without a calculator. So you have to be able to do this all by hand so that you understand doing it. Because a calculator makes your life very easy and you don't think about what you're doing. But let me show you something cool about our nice little Windows calculator right here. Actually, we'll go to the next slide. So it's blank. Here I have my nice little Windows calculator, comes with my calculator. My handheld calculator I don't think has this function, but the Windows calculator does. And if you go over here to View, you can change it to View Programmer. And so if I want to convert a decimal number to some other value, I can. And notice I have Q words, D words, words, and bytes. I'm going to select words. So words are 16 bits. A byte is going to give me an 8-bit answer. A double word gives me 32 bits. A quad word will give me 64 bits. Let's just do word right now. So if I have 98 in decimal, 98, and see I've selected decimal, I can convert it to binary. I can convert it to decimal. I can convert it to octal. I can convert it to hexadecimal. So this little calculator will do all the conversions for you. So, and then your answer, binary, how many bits are shown, I think depends on, yeah, see all of the bits are actually shown down below with all of the leading zeros if you want. A word, yeah, that's 16. It shows 4 zeros, 4 zeros, 4 zeros, and then 0110, 0010, or just a byte for the answer. So your calculator can check all of your answers, but be forewarned, do not do your homework by not doing the calculations. When we do binary math, I think is in the next chapter or the chapter after that, I don't remember when, we'll do binary math. If you do your binary math on your calculator and show me no work, I will not give you credit. So you have to be able to show me the work and not just put it into a calculator. So I wonder if I made a mistake here. Let's check my answer real quick because I got curious because it didn't look right. So let's put hexadecimal, clear, 62 in hex is what in binary? Oh, I have a mistake in there because it didn't come out right. Okay, let's put binary, clear, 100111000 equals. Okay, so in hex, did I? Okay, so let me check my answers because I did not get the right answer. Decimal. Oh, it gives me minus answer because of the leading one. Octal. Binary. Okay, let's check this out. Oh, I know what I did because it was BCD, right? Oops, where's my calculator go? I have to get my calculator back. So if I have, so BCD is not one of the choices on this calculator, so I needed to be careful there. So 98 in decimal, and then convert it to hex, 62, yes, that's correct. Convert it to octal, 142, yes, that's correct. Convert it to binary, yes, that's correct. Okay, so you can check yourself with the Windows calculator. I think that's it for the rest of this chapter.